So yeah, good afternoon, everyone. My name is Juan Manuel Parrailla, and I will explain this research about doing CAs in chemistry. I'm sorry I cannot be there in person. I'm in Glasgow, which is where I live. So just very briefly about the key chemistry in our platform is something which is called the Belousov-Zhabotinsky reaction, which I will say from now on the BZ reaction. I am not a chemist myself, so I cannot offer like a lot of in-depth detail about it. But the interesting thing about this chemical reaction is that the liquid, when it's like nothing is going on, the liquid is in red color. But then if you apply some sort of external method, like we will do is going to stir it, it goes into blue color. So it flashes into blue color in the way that you can see here. So it goes from red to blue, and so on. And it oscillates for a very long period of time. And because it has this sort of like a 0 to 1 oscillations, this kind of chemistry is very commonly used in unconventional computation, which is what we will do in this research. So I guess one of the starting points of our research was this sentence in 1999 by Hoppenstedt, which says that a neurocomputer is a network of oscillators that are connected quickly via common medium forced by an external input. In our case, the oscillators are going to be the BZ chemistry, which I was just explaining now, some kind of like chemistry, which is going to move between two states. And the external input is going to be magnetic stirrers that we are going to put in the chemistry. So the magnetic stirrers are going to oscillate the chemistry, and depending on how the magnetic stirrers is going, the chemistry will oscillate in different ways. And then we will try to put this together into the computations and eventually like CAs. And the platform that we build looks like this one. So here, for example, you can see like 25 cells, which is 5 by 5, and each cell has a magnetic stirrer inside it. Below or underneath these magnetic stirrers, there are like DC motors. So the DC motors are going to rotate, and as they rotate, they are going to move the magnetic stirrer in a particular cell. And as the cell is being stirred, the chemistry in that particular cell is going to oscillate. So the question is, if we have like chemistry in this particular cell here oscillating, how can we transmit information from one cell to the other? So this is just like some pictures again of the platform. You can see, for example, here, like the platform from the top, and you can see the chemistry which is already placed here, and you can see the different stirrers. And I think now this video should play, hopefully. Let's see. Yeah, so this is how you can see the video is connected to some like tubes and pipes. And initially it starts by like putting the chemistry, which is, preparing all the different components in the right way. And then we are going to stir everything together to make sure that everything is like properly mixed. And then we leave it for something like 10 minutes, and then the chemistry and the experiment starts. And in this case, you can see that the left and the rightmost columns oscillate. And you can see how only in those columns, more or less, it goes red to blue. In this video, everything is happening very fast, but in real time, the oscillations take around 1 minute each oscillation, and it oscillates for something like 5 or 6 seconds. And then something quite interesting is that we can control like every stirrer individually. So for example, here in the video to the left, you can see that we enable the stirrers like in a number 1 pattern, for example. So you can see how these ones are enabled, or the one in the picture here, you can see that the ones that we activated are in a sort of like a number 2 pattern. So only those stirrers are connected, and everything else is not oscillating. And we could also connect like we could also control the different speed of the stirrers. Something that we also tried, for example, is to have like the magnetic stirrers in the chemistry connected to the motors, but here is like an open arena, so there is no like boundaries between the different cells as the way that you can see here. And then you can see how the chemistry oscillates, and it makes this kind of like very nice waves. But the problem that we had with this approach is that it was difficult to do like any kind of computation with them, because everything was just like flowing around, and it was very difficult to control. So once we printed the 5 by 5 arena, which was 3D printed, if the cells were not connected between them, so we have this kind of like physical boundaries between them, you can see how like the platform behaves like a sort of a screen where only the cells that are like only the cells that are steering are going to oscillate. So I'm going to play that video again if I can, because it was very fast. Oh, well, it seems I cannot. Anyway. Oh yeah, let's see if it plays again. Oh yeah, and something what was quite interesting is that once you have the chemistry oscillating, as you will see in the second video, once you stop the steerers, the chemistry is going to continue to oscillate in the similar pattern that you were doing before. As you can see here in the video now, how the chemistry is oscillating even though the steerers are not moving. So the idea again is, if we can use all these phenomena that we are seeing, like controlling the oscillations in a particular cell, controlling the way the different oscillations are moved between the cells, and then controlling the memory of the chemistry to see if we can do like some kind of like computation. So the first thing that we did was to implement logic gates, and in particular, we implemented the and or logic gate. And something that perhaps you could see in the previous videos is that the BZ waves that they are recording on the different cells, they easily propagate to the direct neighbors, but they don't travel much far away. So using this property, we can emulate AND or OR gates using the distance between the bits. So for example, in order to simulate the OR gate, we are going to set, for example, in the setup that you can see here, that the leftmost column is going to be the X, the input, and the middle column is going to be the Y, so the second input, and then the column between them, column 2, is going to be the output. And what we found here is that when nothing is happening, when there are no oscillations, there are no flashes in the system. But then if just like the first or the third column oscillate, the oscillations will also propagate to the middle one. So, just by having them close together, you get the oscillations to propagate between them. In order to, implement an AND gate, we did something similar. But here we place like the first column as the X, and we place like the fifth column as the Y. And again, if not, the motors are not steering, nothing happens. But then if only one of the columns is steering, for example, the rightmost column here or the leftmost column here, the signal doesn't propagate to the middle column because, it just loses and dissipates through the space. But then if you have like the leftmost and the rightmost columns, both of them oscillating, because both columns are generating oscillations, they sort of meet in the middle, and then you can see how it sort of, oscillates in the middle. So I think in this video, let's see if it plays. So yeah, this is going to be a quick video of that you can see this kind of experiment. So you can see here, nothing is rotating, so nothing happens. Here, like in the ones in the bottom, only one of the column is oscillating, so it doesn't propagate to the center. Let's see. I'm going to play it again. And then here in the one in the center, because both of them are oscillating, eventually the waves meet in the middle, and the middle column also oscillates. To do the OR gate is very similar as we did before. So in this case, as I was saying, is the first and the third column. If nothing is going on, like if none of the steerers is going on, there are not going to be oscillators. But then you only need one of the columns to oscillate, and the signal will propagate to the center. So you can see here, for example, in the case of the 0, 1, how the center gets to oscillate, and also in the case of the 1, 0, how it gets to oscillate. We also tried to implement an XOR gate, and this was slightly more difficult because, as you know, like you need for them to oscillate when only one of them is oscillating, it's not when both of them are oscillating. So what we did to do this is that we cheated a little bit, because before, when I was explaining the previous video, we were using the distance between the oscillations in order to see if the chemistry is going to mix in the middle of oscillate, but that is not going to work now. But something that we realize is that depending on how you activate the different steerers, there are going to be different waves in the system. The signals are going to propagate on a different way. So you can see, for example, that in the case here, in the case of 0, it's going to be low speed, and in the case of 1, it's going to be a high speed. So you can see that in the case of 0, 1, the signal seems to go in this direction, while in the case of 1, 0, it seems to go in this direction. And something which is quite interesting is that in the case of 1, 1, the signal seems to go from the outside to the inside. So something that we did was to calculate the relative phase difference between between the different as the oscillation propagates through the system. And also we could analyze the way the wave is moving, and depending on the wave is moving, we could say if it's going to be a 1 or a 0. As I said, it's sort of like cheating, but we couldn't find any other way of doing it. So the next thing that we did was to classify the cells, because we are going to need this for the CA, which I'm going to explain just now. The next thing that we did was to classify the different cells, either oscillating or not oscillating. So if the cells are oscillating, it's going to be a blue square, and if they are not, it's going to be a red square. In order to do this, we use like an old school SVM. I don't know, like this is like a technique from the 90s or something, but in this particular scenario, it worked quite well because because the data set is not that complex, and then because it can make a decision very fast, so we can use it for like real-time monitoring. And here there's like a brief description about a CA, but I think all of you know a lot about it, and we are a bit delayed, so I'm not going to explain much about it. But I guess the question is, how can we, use this platform in order to simulate how a CA is going to behave? So here you can see, I'm going to describe this briefly. This is the first CA simulation that we did. So here we have, as I was saying, the 25 cells, 1, 2, 3, 4, 5, and so on to 25. And we are putting them all together like in the columns here. And then, sorry, in the rows here, and then the columns are going to be the time. So you can see here when it's red, it means that it doesn't oscillate, and when it's blue, it means that it oscillates. And so the rule that we are using for this CA is that we are going to set the initial state of the CA. So for example, here we say that cells 1, 6, 11, 1, 6, and sorry, I have a bit of a messed up here. We say that cells like 1 and 5 are going to oscillate. So there are going to be only these two cells, the one here and the ones here. And the rule, the way the oscillations are going to transfer is that once the oscillations move to a neighboring cell, we are going to activate that neighboring cell, which means that from that moment on, that cell is going to, oscillate continuously. So you can see, for example, here that, as I was saying, our initial state is going to be that cells 1 and 5 are going to oscillate. And then you can see that then it moves into cell 2, for example, and eventually it moves into cells like 1, 6, 11, and 21. So it sort of moves into this column, and then it just progresses, and eventually around halfway through, it's already like half of the cells are oscillating. And then we get to this state where we get all these different cells that are oscillating. And here you can see like a video of what I was saying before, what I was just explaining. So the cells in red here is our initial state. Our condition for like starting a new cell is that the oscillations are going to move into the new cell. And the moment the oscillations start into a new cell, the motor is going to steer that cell continuously. And this is the second example that we did, just using the same idea as before. In this case, the initial state is going to be like these 3 cells in this corner, and these 3 cells in this corner are going to be on, and everything is going to be off. So you can see how at the start of the experiment, we have like these 3 cells oscillating. And then the camera is going to monitor how the cells propagate into the neighboring cells. And once the SVM detects that a cell that was, marked as red becomes blue, the motor is going to start oscillating there. And I think it's quite interesting that you can see how it gets to this sort of like a steady state, which occupied most of the experiment, where you have like this block of 6 cells oscillating here, but then it seems that it couldn't break through it. And eventually what happens is that these 2 blocks of cells get in sync, so they start to oscillate at the same time. And then the one in the middle between them, which is the one right here, oscillates, and from that moment on, it's going to oscillate the other 3. And here you can see, let's see if it plays a video of that. So you can see, as I was saying, like only these 6 cells are going to oscillate at the beginning. So now the motor starts to, move them, and they start to have oscillations, and then easily the cells that are neighboring to them start to oscillate, so they also become one, and eventually they transmit the signal to the one in the center once they become like sort of in sync, and that's where the other cells are going to continue oscillating. So in summary, just at the very end, we built a platform to control how a chemical oscillator oscillates between 0 and 1, similar to electronics. Using the distance between the cells, we could simulate AND or OR gates. And then we also did like pattern recognition for an XOR gate. And finally, we used this kind of like behavior to simulate a cellular automata. The main drawback of our research, and something that we couldn't do, even though we tried quite a lot, is that we did not manage to disable a cell. And as you know, in all the cellular automata, like the game of life of so, there are going to be certain conditions which mean that if a number of neighbors oscillates, it's going to kill one of the cells in the center. But we never managed to work that. Like we never found a way to make the chemistry stop oscillating if a number of neighbors are oscillating. And that's, I guess, something that we will need to, further research how to accomplish that. So thank you very much for listening, and sorry for the delay. And you are free to ask me any questions, or you can contact me remotely if you want. Thank you very much.